Okay, well, welcome to this video. This video is going to look at three sort of quite complicated but interconnected things. It's going to look at water budgets, river regimes, and storm hydrographs. And basically, by the end of this lesson, you're going to know what we mean by water budget. You're going to understand the factors that affect a water budget, and that in turn feeds into understanding river regimes and how they vary around the world. And then we're going to look at a particular type of I suppose it is a regime, if you like, what's called a storm hydrograph, which is something you looked at GCSE, and we'll look at, again, reasons why they vary between rivers. So there's quite a bit to get your teeth into. So you do need to take your time over this video. You need to stop. Perhaps it might even be worth breaking into those three bits. But let's get started. So first of all, let's introduce a concept of a water budget. Now, a water budget is basically, well, it's this formula. It's the relationship between the amount of rain coming into a system, the amount of water being lost from a system, and basically what it says is that the difference between those two things will basically be the change in storage. So if you think about it, let's have a look at this. You've got the amount of precipitation, so that's the water coming in. You've then got some water leaving that river basin through stream flow, which you call Q. Some of that water will leave through evaporation or transpiration, which we call E. And then ignore this bit for now. Basically, if precipitation is greater than those two, well, you're going to end up with water building up in the soil. And if these two are greater than that, then the soil is going to dry out. And that's basically all it's saying. It's that really simple idea that if it rains a lot, the soil's going to have more water in it. And if it doesn't rain a lot and it's hot, there's going to be less water in the soil. Now you do need to actually copy down that formula, okay, in your notes, okay, and you need to basically explain what the formula means. So I'll stop the video here, give yourself 30 seconds, a minute to get that copied down, and then we'll move on. Okay, so again, some key terms here that you're going to need to add to your glossary. So it might well be worth stopping and copying these down when it's convenient for you. But basically, when we're talking about water budgets, then there are sort of four, if you like, things that can be happening. So it can be the soil is getting wetter. There's more water, and that soil is increasingly, and the ground is increasingly absorbing more water because there's more precipitation and there is evaporation. And if that happens, we call it soil moisture recharge. So a bit like recharging a battery, it has more power in it. Soil moisture recharge has more water in it. Now, eventually, if you keep adding more and more water, that soil will become saturated. And now the soil can't absorb any more water. What little water is flowing into the rock underneath is more than replaced by the rain coming down. So you've got saturated ground, you've got too much water. And so we call that soil moisture surplus. Now, at some point, that soil is going to become saturated, but then it's going to stop raining. And what's going to happen is that water will evaporate, it'll be taken up by plants, and those plants will start using the soil in the ground. So we've got this phase where there's water in the ground, but it's being used by plants and things faster than it can actually be replenished by rain. And we call that soil moisture utilization, because the water's being used by plants and things, okay, and the amount of water's going down. Now, if that goes on long enough that there's more water being used than is actually coming into the ground from rain, eventually you're going to run out of water. Okay, at this point, the ground will be bone dry, and we call it soil moisture deficit. So they are the four things that you need to know about a water budget. So like I said, if you haven't, stop the video now, add those four things to a glossary, get those notes down. When you're ready, have a look at what a soil water budget, moisture budget graph looks like. So stop the video, get those down, and when you're ready, press play. Okay, so this is what happens if you plot a water budget across the whole of the globe. So what we've got here is latitude, there's the equator, and you can see where the tropical rainforests are, huge amounts of precipitation. Evaporation's pretty high, okay, but not as high as precipitation. So you end up with a significant amount of surface runoff. If you come over where we live, so we live sort of 50 odd, 60 odd degrees north and south of the equator, and what you'll see is, again, there's more precipitation than there is evaporation across the course of the year. So again, you've got a surplus. If you get into the high latitudes, the Arctic up here, the Antarctic down here, then actually there's very little precipitation, there's very little evaporation, possibly a slight net gain there. Although Antarctica, actually, large parts of it, there's actually more evaporation than there is precipitation. That's technically a definition of a desert. But what you'll notice is that there's these two big areas, okay? And these two big areas are sort of 15, 20 to about 40 degrees north and south of the equator. This is where the deserts are. And this is where evaporation is much higher than precipitation. So you actually have a situation where over the course of a year, you actually have a negative water balance. And that's almost, that is the definition of a desert, something that has greater evaporation than precipitation. So what you need to do now is use this information. You're going to create to plot the data on your own world map. So what you'll find is that you should have in your worksheet a world map. Looks slightly like the one we've got here. Let's have a look. And what we want to do is use the information you've got over on the graph we saw on the last slide in the top left corner here. I'm going to plot some data. Now, if you look at that graph, what you'll see is that between 0 and 15 degrees north and south of the equator, roughly, this sort of band here, where the tropical rainforests are, is actually got a net surplus, has more rain than it gets evapotranspiration. And yeah, that makes sense. Yeah, look, you've got the sort of Amazon over here, the Congo here. And likewise, from about 40 degrees north and 40 degrees south, so that's about here, you've got a net positive, a net surplus. So we'll colour that in blue. And again, if we look down here, we'll see that it's about here. Oh, I can't draw a straight line, but you get the idea. And okay, be careful, because actually parts of Antarctica are technically deserts. They have almost zero precipitation and almost zero evaporation, but ever so slightly more potential evaporation than precipitation. But the main deserts, what we think of as the hot deserts, those areas where there's real potential water shortages, they're located here. Okay, in this sort of zone in the sort of tropics. And that's to be expected. These areas are dominated by high pressure, dry weather. They're near enough to the equator for there to be high temperatures, so there's significant rates of evaporation. And if we have a look, what we're talking about are these sort of zones, coming back to this diagram up here. Okay, and if you think sort of Sahara Desert located slap bang there, be about there. Okay, so if you look at the Australian outback, the Great Australian Desert, again located about here, sort of what we've got down here, Atacama Desert, Namibian Desert, the Gobi Desert. All of these deserts tend to be located in these two zones, and that's just reflecting the global circulation model. And if you remember, we did this at GCSE, and it basically says, look, on the equator, it's very hot, the air is rising, and where air rises, it cools, condenses, and it's going to form rain. So that's my rain cloud. Okay, you can see why I'm not an art teacher. And then on the tropical Cancer, it will fall. So what you've got here then is a way of showing how the global budget changes from north to south, from the equator up to the poles. So have a think about, get that drawn, and then have a think how that might affect rivers. So some rivers, like the Nile, for example, actually start near the equator, okay, not far off the equator in Kenya, and will flow north all the way up to the Mediterranean. So they start in a zone of surplus, but end in a zone of deficit. So actually, unlike most rivers, which tend to get bigger as they flow downstream, the Nile will get smaller. Okay, again, you think of something like the Amazon, The Amazon is entirely within that zone of surplus. It's just going to get bigger and bigger and bigger. So when we look at rivers, this is really important. So stop the video, get your world map coloured in, and when you've done that, what we're going to do is we're going to have a look at not just it on a global scale, but how it varies from month to month on a local scale. So this is a diagram that is what is most commonly known as a soil moisture budget. And what we need to do is we need to understand it. So let's talk through it. And then your job is going to be to match up the letters here to the right boxes. So what actually have we got? Well, the top tip with any sort of complex graph you get at A level is to look at the key. So you've got monthly temperature. So we can see that here. You probably won't get that in the majority of soil moisture budgets, to be honest, but it is on this one. Then you've got potential evapotranspiration. And here it is. And you can see what we've got there. Then you've actually got precipitation, and you can see it's a blue line here. Now this is, again, it's worth looking at what we're talking about. We're talking about Southampton, so we're talking about southern England. And this is a pretty typical sort of graph, I suppose, for sort of British soil. Think about the weather. It's wet and cold, coldish during winter and the start of spring. It's warmer and a bit drier during summer, and then during autumn it gets colder and a bit wetter. So you've got that basic pattern. Now, the next thing you need to understand is that there are effectively 4 parts of the story. And they'll be the 4 parts of the story we talked about right at the start. Okay, so by the time we get to January, it's been wet and miserable for most of winter. Precipitation is greater than evapotranspiration, and that basically means that what you're going to have is lots of rain falling on saturated soil. So what you have here is a water surplus in the soil. The soil can't absorb as much water as there is rain. And that's going to happen from, well, any time in the start of winter all the way through to spring. And then in spring, it's getting warmer. So it's getting warmer, so the amount of evapotranspiration is increasing. And evapotranspiration, remember, isn't just evaporation, it's also the plants. So at this point, you've got the trees will start growing leaves and things, so the amount of transpiration is increasing. And this point here often happens in about April, is the changeover from when precipitation is greater than evapotranspiration, and that's changed, so now evaporation is greater than precipitation. And what that means in this zone, you've now got moisture in the soil still, but more of it is evaporating, more of it's being used by plants than is actually being precipitated. So the amount of water in the soil is actually going down in this section. So this would be your soil utilisation stage. Now, it doesn't happen every year, but quite often, eventually, that evapotranspiration, that use of water will carry on until at some point, and this is this point here, the soil is totally out of water. It's now bone dry. And what you've got is a soil moisture deficit. There's still some precipitation, but basically as soon as it rains, that water is sucked up by plants or evaporated, and the soil is going to remain dry. And that's when you might see cracks in the soil and things like that. So here, what you've actually got is a zone where there's pretty much zero water in the soil. Now, what will then happen is that as summer turns to autumn, temperatures will get colder and the precipitation will increase. And just like we saw over here, you get a crossover of those 2 lines. At this point, there is more water entering the soil from precipitation than is being used. And that means that the soil will start absorbing water again. And in this zone, okay, what we call the recharge zone, okay, the soil is getting damper and damper and wetter until eventually we hit this line and basically the soil can't absorb anymore. Okay, it's got to full capacity, you have a surplus again, and the whole thing repeats itself. So I've gone through and spoken through it. What I want you to do now is look at the diagram, and fairly simple. here you've got the letters A, B, C, D, E, F. You've got to match them to the boxes, and you've got to try and remember what these are here. So stop the video for 30 seconds, minute, whatever long it takes, have a go, and then we'll go through it. Okay, so let's just quickly go through it. So A, like we said, is water surplus. The soil is saturated, you're going to get more overland flow, you're going to get puddles of water on the surface because there's more precipitation than there is water being utilised, being evaporated, whatever. So basically there's nowhere for it to go. And that's why floods are most likely to occur in winter. Next we get to zone B, that's our soil moisture utilisation. So now the plants are using more water, the evaporation is taking more water than the precipitation is able to do it. So the soil is becoming drier. Eventually, at point C, okay, there is no water left in the soil. Okay, and by this stage, rivers will start to suffer. Rivers will be at the lowest or low point. Plants will suffer. The soil might start to crack. You'll start to notice it, and that's because you're in this zone D, this soil moisture deficiency. Okay, you basically have very little water in the soil, and then by autumn, precipitation increases, evapotranspiration decreases. You've got that recharge, and eventually, when we get to F, that's when the soil's reached its capacity, no more water for it to absorb, and we're all the way back to A, that water surplus. So that's what that graph is showing. Okay. Now, what you need to be aware of is different graphs will have different patterns. So let's just make sure you fully understand. So what I've got here is another graph. It's probably not too dissimilar from a British one. Okay, 750 millimeters of rain, might be slightly to the west of us, perhaps slightly to the north. Same pattern you'll notice. Okay, so you've got a surplus. This one, the surplus is actually a bit later on in the year. Utilization, moisture deficit, okay, and then a longer recharge. So the same basic 4 zones, slightly different pattern. Right, have a look at this. Now there's no necessarily right answer here. Okay, but what I want to do is just decide which month do you think these statements might be. So Carol's plants are wilting, for example, is letter A. Well, that suggests they haven't got enough water. So it's presumably going to happen at some point during the deficit. So I would, for letter A, I'd probably say, oh, August would be a sensible thing. Now, stop the video, have a go, and see what you come up with. Like I said, there's no right answer, but I'll talk through what I would put down. So stop the video, have a go, and we'll start in 30 seconds or so. Okay, so we've done A, and we said that was probably August, might be early September. What about B? The local river is in flood. Well, that's going to happen when you've got too much water. It's going to happen when there's a surplus. So that's going to be any time from February up to about April, February, March, April. Puddles can be seen on the surface of the soil. Well, again, that has to be that same pattern, isn't it? You wouldn't have puddles on the soil because unless there was actually a surplus, because if not, it would infiltrate quickly in. So B and C have got to happen in that period of surplus. A hosepipe ban is lifted. Well, that means that there was a shortage of water, but there isn't any more. So actually, it's probably going to happen at some point from, well, I suppose October, possibly through to sort of February, when basically there's more moisture and there's more water. A hosepipe plan is put in place. Well, that's got to happen at some point after evapotranspiration is higher than precipitation. So it's going to be any period during this point here, probably during the deficit you would have thought. So again, June, July, August, September would be the sort of phrase. It's rained all week, but there are no puddles on the ground. So for this one, I'm thinking, well, hang on, if it's rained all week, precipitation's obviously getting higher, but there aren't any puddles on the ground, means that the water's infiltrating into the soil. So that would suggest that it's during the recharge. So October through to sort of February on this one. And this one, it's been dry for 2 weeks, but the crops look healthy. Well, that suggests that there's water in the ground, but the precipitation is going down. So I would have thought that that's going to be the sort of soil moisture utilisation. So sort of March through to sort of July sort of time. But like I say, as long as there's a logic behind it, you've got it right. So that's a similarish one to what we've seen. Now let's have a look at a slightly different one. And this is for you to have a think about. Okay, you'll notice it's got the same four zones. So recharge, surplus, utilization, deficit. What's different about this? Can you annotate this? Okay, can you pick out the key bits? And how's it different from the one we saw in Britain? Just stop for a second and see what you've actually managed to annotate that with. Okay, so what differences did you notice? Well, the first thing you should notice is that actually, look, the annual precipitation is 989 millimeters of rain. That's about 50% more than we get in Bicester. But the evapotranspiration is 1782 millimeters. This is a desert. Okay, this is technically a desert. A desert is when there is greater potential evaporation than there is precipitation. And actually, what's unusual about this one is that actually it's the other way around. So most of the time, okay, if we look, evapotranspiration is actually higher than precipitation. And what that means is that there's only a short period of time here when there's any moisture in the soil at all. From December all the way through to June, July, actually there's a soil moisture deficit. So this would be somewhere, I would guess, well, looking at it, it's got a wet season in August. It's going to be just north of the equator. It might be sort of Kenya, somewhere like that. And actually, the first thing you annotate is that this has got a long dry season. This would not be a good place to be a farmer. You're going to struggle to actually grow crops during this period of time. You've then got a short wet season. Like I say, you're sort of coming from June all the way through to October, about 4 months when you've got some half decent rain. You've got a relatively short period of recharge. You've got certainly a short period of surplus, and then you've got a couple of months here of showing soil utilization. So this is different from what we saw in the UK. In the UK, we saw a long period of soil moisture surplus. It took a while for it to recharge. It took a while for it to be utilized, and the deficit was actually relatively short. Here, it's the opposite. Okay, so this is typical of a tropical sort of savanna type soil. Like I say, like you might find in places like Mexico or in places like, I don't know, Kenya, sort of just say central northern Africa, south of Sahara, what called the Sahel. So just to make you realise that you can get very different soil water budgets. Okay, so let's move. Now, the idea of looking at the soil water budget is that it tells you how much water is in the soil, and by default how much is flowing into local rivers. And so actually with rivers, what we often talk about is something called a river regime. And again, what you'll need to do is you'll need to add this to your glossary. And it's basically the average flow in a river over a year. Now, that water will get in from what we call direct precipitation. Okay, so it rains in the river, surface runoff or overland flow. Okay, or it will seep in from the ground water or through flow. Right, have a think. How many different factors can you think of that are going to affect a river regime over a course of a year? And there's a few photos there to hint. So have a go at that. And then in a second, I'm going to get you to read a bit and see if you can add anything else. So stop the video. When you've thought of as many as you can do, press play. Okay, so this is a photocopy out of the textbook, so I apologise for the slight sort of shading there. What I want you to do now is have a read through this, and then hopefully you've got something like this already drawn up, but I want you to make a list of all the different factors, and basically it's the bullet points here. And you might want to take and develop them further, but you need to have some decent notes explaining what factors will affect river regimes. So have a read through that, stop the video, and when you're ready, let's have a look at what different river regimes around the world look like. Okay, so hopefully you've got a whole host of reasons that are going to affect the river discharge. It might be the vegetation, the urbanisation, human use, the geology, the relief. All of those factors are going to play a part. But the most important is probably climate. And what we've got here are four sets of um, river regimes. Okay, I've got one up here. This is the Rhone, for example. I've got one here, which has got the Thames and the Seine. I've got one here, which has got the Blue Nile in there. I've got another one here, which has got the Durance and the Rhys. What I want you to do, and they represent sort of four classic types of river regimes. You've got European glacier melts. So which ones of these do you think are rivers that are fed by glaciers that are melting? You've got ones that are fed by snow melt. And actually, to be fair, these two are going to be very similar. So if you get these wrong, I'm not going to be upset with you. I think they're almost effectively the same. You've got oceanographic rain. So this is rain coming in off the ocean. So it's what we get in Britain, for example. There's a big clue there. And that's going to be affected by the amount of rainfall and the evapotranspiration. And then lastly, you've got tropical seasonal rainfall, sort of monsoons, what you might find in India or say parts of Africa. And again, there's a clue there. So just have a think and see if you can actually work out which one goes with which. So stop the video. When you've had a go, we'll go through it. Okay, so that's the first one. So European glacier melt. So what's happening here is that the river is basically getting its water from glaciers that are going to melt in summer. And it's going to be sort of greatest when you get at the end of summer most of the time. So it's going to be sort of June, July, August. So if we have a look, what we'll see is got it. It's going to be this one up here. And this is typical of glacier melt. So if we take this one here, the red one, most water coming in sort of August and July. This one's a little bit early as July, August, perhaps it's slightly further south, who knows. But basically that's typical. Yeah, lots of water during the summer months, very little elsewhere. Now, if we come to look at oceanic rainfall, okay, evapotranspiration, we're talking about British weather, for example. And we know that it gets a bit wetter in winter. It still rains during summer, but actually evapotranspiration increases. So you'd expect there to be an increase in flow during the winter months and a decrease in the summer. And yeah, if you have a look, that's quite obviously going to be this one up here. And in fact, you've got the Thames there as the classic one, which basically has got very low flow rates during summer, much higher during winter. And then we come back here, we've got snow melt. Okay, and again, that's going to look very similar to this. Okay, it might be more spread over a longer period of time, but it's going to be similar. You're going to have a peak during the summer months. Okay, so again, if we have a look, what we'll see is that no surprises, it goes to this one. If we look at these rivers here, you might find these in sort of, I don't know, parts of Northern America, Russia, parts of Europe where you perhaps get heavy snow during winter. Okay, you're going to get that sort of pattern. So again, very summer. Okay, basically the same process. It's snow and ice turning to water during the summer months. But this one's slightly different. Okay, this isn't snow. If you look at the Nile, for example, we'll get some snow from mountains in, for example, I don't know, Ethiopia. But the Blue Nile, okay, is predominantly fed by tropical rainfall. And what that means is that you'll get this, again, distinct increase during the wet season and very low flow during the winter seasons, or the dry seasons, sorry. Okay, because obviously in a tropical climate you tend to have two seasons, a wet and a dry season, rather than be winter and summer. So this final one is typical of that. So what I want to do is get these labelled, and then next to them bullet point so key information of each one. Okay, and when you've got that done, I say pause the video. When you've got that done, let's go on now and have a think about how rivers react, perhaps on a smaller scale. So now we're coming to the third and final big concept of this video, and these are flood hydrographs. And what flood hydrographs show is the flow in a river, but over a short period of time. And there's a lot of information here, but hopefully absolutely none of this should be new. You should have covered this at GCSE, and there really isn't much to add to it. So the first thing to understand about this is it's got lots of lines. So the green line is the discharge, and discharge is the amount of water flowing through the river, and it's measured in cumecs. Okay, and you can see it here. And cumecs stands for cubic meters per second. Again, add that to your glossary. In fact, all of these terms will need to go in the glossary in a second. You'll see on the worksheet there's space for that to go. Then you've got these bars. These bars represent precipitation. And again, you'll see that that's shown here on the scale. So there's actually two scales here, and you need to be aware if that gets a bit complicated. Now, the discharge is often split into two. So you've got base flow. Now, this is the water that gets into the river through the ground flow, through flow. So it's not getting into the river quickly. And then you've got storm flow. Now, storm flow is water that's getting into the river quickly. It's coming in via overland flow or surface runoff, whatever you want to call it. And some storm hydrographs show the difference, some don't. Okay, again, depends what happens in your exam. But what you'll see is that most storm hydrographs have got this pattern. It rains, the water goes up, and we call that water going up the rising limb. It'll hit the peak, and because of the peak in discharge, we're unimaginative, we call it the peak discharge, and then it will fall. And again, as it's falling, it's called a falling limb, and it'll go back down. And it may follow this pattern, it may be sharper, it may be flatter, but that's the basic pattern. You're often asked to calculate this, the lag time, and that's the gap between peak rainfall and peak discharge. And we use that to classify the type of hydrographs. And basically there's two types. There's a flashy hydrograph, which means that the lag time is very small, and there's a slow onset one, which means the lag time is very long. So that's the key terms. So your job now is that you should have this sheet, and what I want you to do is simply go through and match up the key terms to the definitions. So for example, the time difference between peak rainfall and peak discharge will be the lag time. Okay, the highest amount of rainfall per unit time will be the peak discharge. So quickly just get those written in, okay? And once you've got that done, we'll then make sure that you can understand what these actually are showing. Okay, so we've got two hydrographs here, and like I say, you've got the classic two here. So what you'll see is you've got a relatively flashy one with a short lag time, and you've got a slow onset one with a long lag time. And all I want you to do now is have a look at the next sheet. In fact, let's move on to that. And you need to basically decide which factors will make it flashy and which will make it slow onset. And this is where you need to do some extra reading. And you've got a geofile that's been emailed to you. Have a read of that. Use your own common sense. You know, if you think of rainfall, what's going to create a flashy hydrograph? Well, it's going to be intense, short bursts of rain. Antecedent conditions means what's the ground like beforehand? And obviously, if you're in a zone of surplus where the the ground is saturated, it's going to encourage more overland flow, so there's going to be a flashy hydrograph, and that's the key. Things that encourage overland flow will increase the chances of being a flashy hydrograph. Things that are slowing the water getting into the river will create a slow onset one. So use that and fill that in for me. Okay. Shape of the river basin is a bit more complicated than some of the others. The others are fairly simple, but as a rule of thumb, the sort of rounder and sort of more rivers there are in a small area, what we call the drainage density, the more flashy. The longer and the fewer rivers, the lower drainage density, the less flashy, the slower the onset will be. So go through, you have to stop the video, do your extra reading, and when you've got that done, let's move on. Okay, so we're coming to the end of the video now, and just a bit of homework for you to do, just a couple of quick exam questions. And what you've got here are two storm hydrographs, and you've got a map showing where the two streams are. You can see they're really close to each other. And you've got a key. And what you've got to do is you've got to contrast the hydrographs, and then you've got to explain the contrast between them. So one's asking you basically to spot the difference. One's asking you to basically explain those differences. So in terms of differences, well, what is it they're asking you to do? Well, the obvious thing here is, again, is to think about the lag time. Slow onset. So if you have a look here, you can measure a peak discharge is about 2 hours. Peak discharge, sorry, peak rainfall 2 hours, peak discharge about 20. So there's an 18-hour lag there. Over here, again, same peak rainfall, but this time peak discharge is about 8. It's about 6 hours. So much more flashy discharge. The other thing is different is that the actual peak discharge, again, hits 10, over here hits 25. So you can pick out these sort of differences. You might want to think about the shape, okay, about the angle of the rising and the falling limbs. So that's the first bit, and that really is just spot the difference. But the second one is asking you to think about, well, why is that flashy? Why is that slow onset? And the key here is this map. Now, I could answer this question without even looking at the map, because actually the answers here are on the key. Okay, without looking at the map, oh, impermeable. I know impermeable means that water can't soak into the soil, so it's more likely to increase overland flow. Well, I'm guessing, without looking at the map, that will be Ostrich Beck. So have a look at Ostrich Beck, and we can see, oh, look, impermeable. Okay, in fact, I've got it wrong. That'll teach me. Actually, it's impermeable shales. Okay, but I've got permeable limestone. Well, my guess would be that would be the slow one, and I am right here. Look, this water, this river flows into the limestone, goes down a pothole, and comes out at Clapham Cave, and then flows on here. And in fact, this is a famous sort of caving area. In fact, I've caved in a number of the areas here. There's lots of underground water and rivers in this whole network here. I've got woodland, and again, woodland, that's going to increase interception, might increase transpiration rates, although it's mainly to do with interception. Again, my guess would be that that would be in the slow onset one, and look, yep, I'm right. A stream, well, they're both streams. Artificial lake suggests perhaps there's man-made sort of management there, and again, I would guess that's in the one with the slow onset, and I'd be right. So it's really, the key here is look at this, use those to explain them. 5 marks, I would expect you to talk about 3 different things. So that would perhaps be the soil type, the sort of rock type, the woodland, the artificial lake. 3 things, explain those and explain it, and you'll be fine. So have a go at that. And if you're interested, what I've got here is a sort of mark scheme and a sort of key information. So you can use that there when you finished it to actually mark it yourself if you want to have a go. Right, so that's the end of this. So hopefully that's been useful. If there are any questions, by all means, email me as ever. Ping me the answers when you've got them. Make sure you've done your background reading. Now, not only is there background reading on the hydrographs, but also there's another document I want you to read as well. So make sure you've gone through that and taken notes, and you've got your glossary up to speed. Right, hope that's been useful. Any questions, email me. And until next week, I'll say goodbye.